In this video, we'll take a look at graphs of sinusoidal functions and how do you find an equation given the graph. So we'll review a little bit what the graphs of sinusoidal functions look like, or the equations. Y is equal to a sine bx minus c plus d, or y equals a cosine bx minus c plus d. So if we're working backwards and starting with the graph and trying to find the equation, we want to find the values for a, b, c, and d. So if we take a look at the graph that we're given, first of all, determine if you want to use sine or cosine function. So the sine function starts, just a reminder, your sine function starts at 0, 0, and your cosine function starts at 0, 1. So this function looks closest to the sine function. It looks like it might have started at 0, 0 and moved down 1. And it also looks like a reflection. So we'll use sine since it looks like a reflection of the sine function. So our goal is to find y equals a, b, c, and d in the sine function. So the first thing we do is draw in the midline, and this value is d. So the midline is what cuts your graph exactly in half horizontally. The highest value in our graph is at -3, 5. Our lowest value is at 3, -7. So halfway in between 5 and -7 is right here at -1. So at -1, that cuts our graph in half horizontally. So that's called the midline. And the midline for our graph, the value is d. So y equals -1 is the equation for the midline, and d is equal to -1. Now find the amplitude. The amplitude is how far you're going from the midline up and down. So if you know the maximum and the minimum, subtract those two values and divide by 2. So the maximum is at 5, the minimum is at -7. So we're going to take 5 minus a -7 and divide by 2. So 12 divided by 2 is 6. So the value A, the amplitude, is 6. Since this is a reflection, we're going to let A equal -6. The amplitude is 6, but A is going to be -6 for the reflection. All right, the next part, determine the period so that we can find B. So 1 period of the sine function, if we start here, and it will end back at that midline, we go from 0 to 12. The period is 12. So to find b, we take 2 pi over b is equal to the period, which is 12. And then we solve for b. So you can think about that as 12 over 1, cross multiply. 12 times b is equal to 2 pi. Divide both sides by 12. We get pi over 6 is equal to b. A is -6, d is -1. So the last thing we have to find is that whether the graph has a horizontal shift or not. So if you take a look, it doesn't look like it. It starts at 0 and the sine function starts at 0. So we haven't done a phase shift. So in this case, C is going to equal 0 because we have our phase shift is 0. So what's the equation for our line, or our function? Our equation is going to be y is equal to a, which is -6, times the sine of our b, which is pi over 6, times x. We don't have c, and then -1. And then to check and make sure you're right, you can type this into Desmos and make sure that that's the graph that you get. Okay. All right, next example. Let's do that again, but let's use cosine instead. So the cosine for this one would start here and end here, okay? So we go through the same steps as we did before. Step 1, draw the midline, and that value is D. So the midline, our highest value is 8, our lowest value is 0. So the midline would be y is equal to 4. So that tells me that D is equal to 4. The graph is moving 4 units up. Then let's find the amplitude. Find A. So how far are we going from the midline up to the maximum and down to the relative minimum? Well, if that's a total of 8, we take the maximum of 8 minus the minimum 0, divide by 2, and we end up with 4. So this case, the amplitude is 4. It's not a reflection of the cosine, so it's a positive 4. Then we find B using the period, knowing that 2 pi over B is equal to the period. So if we take our starting value to our ending value, it looks like we're starting at 3.5 and we're ending at 13.5. So the period is 10. That's taking 13.5 minus 3.5. So 2 pi over b would equal 10, the period. Then cross multiply. 10 times b is equal to 2 pi. Divide both sides by 10. So b is equal to pi over 5. Then this one does have a phase shift. So if you take a look, the graph starts here at 3.5 instead of starting at 0. So this is actually moving to the right, 3.5. So to find C, we know that the phase shift is equal to C over B. So we get 3.5 is equal to C over whatever B is. And B is pi over 5. So we get 3.5. I'm going to write it as a improper fraction instead. 3.5 is the same thing as 7 over 2 is equal to C over pi over 5. Multiply both sides by pi over 5. These cancel. I get pi over 5 times 7 over 2 ends up being 7 pi over 10. And that's what C equals. So now we can put it all together in the equation. So we used a cosine. So y is equal to the amplitude, which is 4, times the cosine of b, which is pi over 5, times x. We're moving to the right, so we have minus 7 pi over 10. And then our entire graph is moved up 4. So that's our finding the equation if you have the graph. All right, there are two applications I want to take a look at. One of them is the daily temperature in the month of March in a certain city varies from a low of 24 degrees to a high of 40 degrees. Find a sinusoidal function to model the daily temperature and sketch the graph. Then we're going to use the graph to approximate the time when the temperature reaches the freezing point. So I've got the solution shown. The first thing we do, if you know that your daily temperature is going to be over 24 hours, so let me scroll this down so you can see. The daily temperature is between 24 hours, so you know that the period is 24 hours. We have a low of 24 and a high of 40, so the midline would be halfway in between there. We know the midline would be y is equal to 32, so that would be 40 plus 24 divided by 2. That's the maximum. It's 32, so that's D. So let me write it down. D is 32. Then the period is 24. 24 is equal to 2 pi divided by b. So cross multiply. 24b is equal to 2 pi divide both sides by 24. B is equal to pi over 12. So there's our pi over 12. There's our 32. And the amplitude is from the midline to the maximum or the midline to the minimum. The total distance between maximum and minimum, so the amplitude is 40 minus 24 divided by 2. So that would end up being 8. So the amplitude is 8. And that's where we get that function. And then you can see the temperature reaches freezing, 32 degrees, at noon, and again at midnight. All right, other application we'll take a look at is something called simple harmonic motion. So think about simple harmonic motion involves restoring a force but assumes the motion will continue forever. So if you have a weighted object on a spring, when the object is not disturbed, it's at rest or in equilibrium. If we pull the object down and then release it, the force of the spring pulls the object back towards equilibrium, and harmonic motion B begins. That should be B. E begins. The restoring force is directly proportional to the displacement of the object from its equilibrium period. Point. So think about if you have an object on a spring, you pull it down, and then you let it go. The object's going to just move up and down, up and down, up and down. And what that means over time is it moves up and down over time. So you can model it with a cosine function or a sine function, and the only two things we look at are amplitude and period. So the amplitude is still the absolute value of A. The period is 2 pi. It's a different variable, but it's still the same idea. And then a new introduction here. If you take 2 pi divided by W, the period, and you flip it over, W divided by 2 pi is the frequency, or the number of cycles per unit of time. So the example for the given function, we have y equals 5 times the sine of 3t. Find the maximum displacement of the object. The maximum displacement of the object is the amplitude, which is 5. Find the period or time required for one vibration. The period is 2 pi divided by 3, because that's what B is in here. 2 pi divided by 3 is the period. And then the frequency is the reciprocal of the period, which is 3 over 2 pi. Then you can take a look from the graph what that object looks like in simple harmonic motion.